Yeah. Hello everyone. This would be the first video in the series CUDA Programming Part 1. And what we are trying to achieve with this, on each day for the next 30 days, I would upload maybe a short video on CUDA or maybe a 1 hour lecture or anything, um, covering different topics and all. I do not claim to be an expert in this field. So what I'm trying to do is document my journey regarding the learning process and what my current understanding of this is. So I guess that would be helpful for a lot of folks, and they can also watch the videos and try to understand if they're trying to learn CUDA on their own, what topics do they need to study. I'm not saying that should be the final roadmap. I have some topics in my mind, and I will be following those topics religiously for at least the next 30 days, although the plan is a little bit bigger, maybe till the end of December this year. So in the part one, okay, before moving on, I would like to say I don't want to discuss a lot of theory in this. I just want to keep these videos as practical as possible because I myself is not interested in a lot of theory. I just want to quickly go and build stuff and understand how it is working on the device. Okay, I have said the first fancy word device here, but we will discuss all of them together. So I don't want to discuss a lot of terms. I'll just directly jump to the code and we will understand what each line of the code does. So let's see. I hope this is visible. Let me zoom in a bit. So this is basically a hello world, if you can say, for writing a CUDA C program. And how will you interpret this is my question. Before moving on, what exactly is CUDA? So it is a interface provided by the NVIDIA smart guys and girls at NVIDIA, allowing us to use their GPU hardware at much lower level. We can manage threads, blocks, grids, schedule a lot of operations and everything, and basically utilize the GPU hardware at a bigger scale or a better level. So my understanding is you have a CPU and a GPU. If you have a lot of tasks that you need to do in parallel, if you have to invoke a million threads or something to do a particular step, use a GPU. Otherwise, CPU is a lot good to do a lot of stuff. But let's say you are making a fluid dynamics engine or even a simple physics engine, which is calculating, let's say, position or anything for a lot of bodies. Let's say a 1 million bodies that you have. Now, you won't be able to do a lot of these calculations in a CPU. It will be a little bit slow. That's why people move on to GPUs and try to parallelize a lot of their stuff so that they can achieve a better speed. They can write their stuff very fast. But even in that case, if you're watching this video, I understand that you would know that why to use a GPU or anything. The gaming people, the gamers know about it a lot. It will basically make your stuff faster. But how does it do it? Uh, how do we utilize it? It is a separate different matter. So let's say, um, if it is a CPU, it will have, let's say, around 8 threads, if we can assume. Do not quote me on that number. 8 threads to do parallel computation, and if we have a GPU, it will have a million of them. It does not have a million, but basically a very very huge number of those threads, and you can invoke each thread, and each thread will call a kernel separately. Now, I am using the word threads a lot, and you will also realize that while we try to understand the Hello World code, there is a lot of stuff about threads and blocks and everything. So basically, first we need to understand what a thread is. So it is a single most smallest the component or a piece of computing, you can say. So suppose uh, if you are on a CPU, a thread can be, let's say you are using Spotify. A thread can be play a song, or what happens when a user pushes a like button. So all of these are processes let's say, just assuming these are processes and they will run side by side, they will run parallelly, and each of them will be using their own thread to run that. But a thread on GPU is a little bit different, but the overall concept is same, that it is the single most smallest unit of computation. And how do we visualize it? So suppose you have a vector 1, 2, 3, 4, 5. So we have 5 elements. Now suppose you invoke and say to the device. What do we mean by device? Device is nothing but your GPU. What do we mean by host? Host is nothing but your CPU. Just remember this stuff. Not a lot of importance, but it's fine. So suppose we say that invoke 5 threads on the GPU. I hope I'm recording, but because I will be very disappointed if I don't. 5 threads on the GPU, and each thread will be accessing individual elements, right? One way to do is sequentially. There is only one thread, right? And it is first reading this one, then reading this element, then go to third, then goes to fourth, then goes to fifth. It will be pretty much very slow. So, but what if you had 5 threads and each of them are accessing at the same time, or reading these elements at the same time, or updating these elements at the same time? That would be pretty fast, right? And suppose if there are millions of them, a million threads, that would be even faster, right? So you have some sort of a computation, you have a thread, and you will have multiples of such threads. Now, one thing to understand is the instruction can be same, but they will read different parts of the data. I'll just rewrite it down. Reading different data, because it makes sense. Otherwise, what is the benefit of even parallelizing your stuff? In applications such as machine learning, or right now LLMs, you need to train a lot of stuff. There are billions of tokens, there are billions of parameters, and if you're optimizing it on a very low level scale, you are optimizing a matrix multiplication, and there are, let's say, n cube is the time complexity of a matrix multiplication. N is very small in this case, just 1024. It still is what, 10 to the power 9 operations, which is huge. In that case, you would like that a thread can access a row, another thread can access the column, and we can just multiply them together and aggregate the sum in some variable, right? You can do that too. So that makes sense. So the instructions are same, that first thread can have first row and first column, second thread can have second row and second column, something like that. So all of that calculation stuff is very trivial. I'm not going to go into that. But my whole point is this: thread is the most basic uh, unit of computing. Consider it like the atoms of computing, which I guess is wrong to say, but yeah. Now, what we are doing in this code is, you will see that we are defining something called a hello. Let's look at this first. Now, there is a special keyword which you will not see in your normal C, C++ code to use a global keyword. There are two more keywords like this. First is device, and another is, I guess it was host. I've never used those ones, so I may be forgetting about this. Now, the global is something. Each of these keywords tell the compiler uh, some different things about this function. Now, in CUDA, a function can also be called a kernel. So this body here is looking like a function, but they thought, let's name it something fancy, and they called it a kernel. Now, this is just a very basic function, but we are appending a global keyword which tells the compiler. What is the compiler in this case? It is NVCC. NVCC is the NVIDIA CUDA compiling system. Also, you may observe that I'm right now on a Mac. and I don't have the NVIDIA toolkit on it, but I do have some workarounds to run my CUDA code, basically using Google Colab and everything. Well, we will look into that. There are some workarounds if you don't have NVIDIA GPUs as well. You can use a very wonderful service called Lead GPU. So they have their own playground and CLI as well. They also allow us to just check if your code will compile correctly or not, and then you can test it out on real hardware after, let's say, buying something or renting it out. Now, NVCC compiler, it will look at the global keyword, and what it will tell, it will understand that this particular function or a kernel has to run on a GPU, but it can be called from a CPU, right? And what does device, if we just instead type device instead of that, device tells that it can be run on a GPU and can be called from a GPU only. There is no CPU in it. Same goes for host. Host can be run from a CPU as well as called from a CPU, right? So generally people used to try to write a global keyword because it is simple, very easy to understand. Now you will observe there are some fancy stuff that we are trying to do, trying to find some ID of blocks and block dimensions and threads. What are these? So, uh, first let's understand the hierarchy of this model. So we have threads, then we have blocks. We do have warp in between, but it is not important here. Then we have grids, right? This is the basic hierarchy of how computation is taking place in your basic CUDA program. So you invoke a lot of those threads. A group of those threads form a block, and a group of blocks arranged in a particular manner is called a grid. Now, each of them have dimensions associated with them. So there are three dimensions associated with them: X, Y, and Z. Same goes for block, right? X, Y, and Z. So you will also observe in the code there is a special, let's say, keyword for this, or data type for this called dim3. So dim3 helps us to specify the dimensions of a thread or a block, right? So what they also have is each thread as an ID, each block has an ID. So suppose, let's take an example. How do we do it? If we are handling, let's say, 1D data. So generally, when you are writing your kernel, you may be working with 1D data or two-dimensional data or a three-dimensional data set. So in this case, let's just take care of 1D data. We have an array, right? And if you want to do any operation on this array, you would like to invoke a number of threads, right? And each thread will have X components. You will see that we have a thread ID, right? Thread ID dot X and everything. Now, these XYZ are also IDs. In blocks, we have dimensions as XYZ as well as block IDX dot X. So if you want to say which thread to go to or which particular block to read something, you can always do it using thread IDX dot X. Now, if you're using images for this, which have two-dimensional data, you may want to also use something called thread IDX dot Y, or if it is a matrix, or if it is something other than or a tensor, maybe not matrix, which is three-dimensional, you can use the Z component on it. Same goes for blocks. Now, a group of threads form a block. So this is just a block. And a group of blocks, they form a grid. So whenever you are writing out a CUDA program, you need to specify how many threads per block you should have and how many blocks of threads you should invoke. So finally, so let me just write it down. So we need to specify threads per block. This is first important number. Second important number is total number of blocks. And we will see in the code how to do it. Let's go back. We'll start with this part here. Just quickly take a screenshot of this. Okay. Now, what we are defining is the number of elements, or let's say, yeah. So it will be 1 million. Now you will observe that we are defining threads per block as 256.11. So the X component is 256.11 and we are only handling one dimensional data. So it does not make sense to specify the Y and Z dimensions of it. Now we are also defining blocks per grid. So also you may ask, you have arbitrarily written 256 here, but is there a maximum limit to it? So if I recall correctly, on the official documentation page of NVIDIA CUDA C programming, they have mentioned that based on the current compute architecture, the maximum limit is around 1024 threads per block. So we try to be below this, and 256 is a very sweet number, 16 by 16, a whole square, perfect square. Now, we also need to define the adequate number of blocks. So see, there are 1 million elements. There are only 256 threads per block. Now we need to calculate how many blocks we need to invoke such that we have sufficient number of final threads. So total number of threads can be calculated as number of blocks times threads per block, right? So this will give us a total number of threads. So suppose if you want to do some operation on 1000 elements, where n is 1000, and the threads per block you have set it to 200, right? So the total number of blocks that you need is 1000 by 200, 5. You require 5 blocks of each 200 threads, and this will in turn invoke enough number of threads so that your kernel can run for all those n elements. Otherwise, there is a chance to miss the number of elements. So we generally try to, let's say, 1000 number of elements, and we are defining threads per block as 256. So we try to round off the number of blocks so that it is slightly more than what we require. So let's say we invoke 4 blocks. So 4 times 256 is what? 24 to 1024. So you will see we have invoked 1024 threads, but we only require 1000. So these 24 threads will not do anything. It will not access any element. We will make sure of doing the required checking in the kernel as well. Uh, Whereas if you invoked only 3, you will miss it. You will miss a lot of a large number of elements and they won't get updated. So it is better to invoke larger number of threads than missing on them, right? You don't have any shortage of threads, at least for now, right? So let's try to understand this. We have defined a number of threads per block, which is 256. We have invoked enough number of blocks as well, which is basically the formula n plus x minus 1 divided by x, which gives the some sort of a floor above n by x. Just to give you an example, if we have 10 and we need to do it by 7, so we'll do 10 plus 7 minus 1 by 7. It is how much? 17 minus 1, 16 by 7 is around 2, right? So if you had 10 number of elements, 7 threads per block, you would require 2 blocks, which makes sense. And in the final, you will have 4 extra threads. But if you had only 1, you will be short on 3 elements. And 3 elements from the initial list of 10, they won't get updated. I hope you understood the simple basic mathematics that I'm trying to do. Now, let's ignore this part. This is for timing purposes. I'll cover it in the later part of this lecture. But how do we call a particular kernel? So this is the important line. So this is a kernel name, hello. We are defining the blocks per grid and the threads per block. And in these brackets, we'll pass the parameters that are required. In our hello function, there are no parameters that are required. Right? This is a very simple thing. We are not making any memory or host. We are not copying any memory to device or copying any memory from device to host back. We're not doing anything. We will see that in the second example of the code that I have. But first we will try to run this thing as well. Now, where were we? Yeah. So here, if we look, the question is, if you are invoking a larger number of threads, right? How will you verify if uh, you need to update, if a particular thread has to update an element or not? So suppose this is a block. This is a block with ID 1, BID 1, or 0 in this case. This is a block with ID 1. And each block, so threads per block, it let's say 3, right? So we will have thread 0, T1, T2, same goes for this. Now, if you see, this is the block ID X variable that we are using in the code. I'll also take a screenshot again. A lot of stuff to do. Yeah. So if you see, this block IDX is coming from this thing, block ID 0, block ID 1. Same goes for block dimension. Now block dimension is 3. Same goes for this block. The dimension is 3. And the thread index is 0, 1, and 2 for each of these threads. 0, 1, 2. So in the first block, which is 0, index is 0, the threads are 0, 1, and 2. And in the second block, the threads are again 0, 1, and 2. So if you want, let's have a dry run of this thread. We will run this code and understand how it works. Then it will make a lot of sense. But let's see. If you want to access, how will they get arranged, right? Let's start with IDX first. So let's say, what will be the ID of this block? It will be 0 times 3 plus 0. So that is the overall global ID, if you can say. So there are total 6 threads, 3 in first block and 3 in the second block that we have invoked. And if you want to understand what will be the global ID of the first thread, it will be 0, uh, first, second, and now the block ID is 1. 1 times 3 plus 0 is 3, then 4, then 5. So the global ID is 0, 1, 2, 3, 4, 5. And the if else condition that we are doing is basically taking care of the if else condition that we are using is basically taking care that if we have some sort of extra threads, that it should not update the uh, a particular element in the original array as well, right? I hope that makes sense. Let's try to run and understand how it works. So I have this thing in CUDA. So I've already uploaded that code to a particular GitHub repo. So the problem right now I'm facing is I don't have any CUDA toolkit in my local Mac system. I don't have an LSP. So if I save, you will see a lot of errors and everything. So that makes the code ugly. So I just push it to GitHub and try to run it on Colab. So let me just clone all of this again. I hope it runs super fast. Now we have cloned it. You can see the files are day 1 and the second one is the another example that we have. Now the compiler, as I mentioned earlier, that the compiler we used is called NVCC, NVIDIA CUDA compiler. Sometimes you also have to specify the architecture of the GPU you are using. For TPU, it is compute architecture. I guess the current GPU is T4, right? And for T4 GPU, the compute architecture is 7.5. So that's what you are mentioning, 75 here. Then we just then we just mention the file name, the output is in day 1, and then we run it. Let's see what it outputs. Oh, I had to change this thing, right? So you will see we have block IDs, thread IDs, and global IDs. So in the code, you will see block IDs are 256 and everything. It does not make sense, but I have already given the example. So block IDs are 0, thread IDs are increasing in a particular block, and same goes for the global IDs as well. If if you want to access, let's say, how can I edit and collab itself? Since the block dimension is 256, let's try to do 300. I've specified 300 as threads per block. So you will see once we have, okay. Yeah, here it is. So you can see that once we have reached the block ID 1, there are threads that are called, let's say, consider this one. So the block ID is 1, the thread ID is 1, or the block ID is 1 and the thread ID is 0. So the global ID is 256 because 0 to 255 is in the first block, and starting 256 is the second block, which has the block ID as 1. So I hope you understand what I'm trying to say. Now, moving on to this code to understand how timing is working. So in CUDA, to time stuff, you need to create events. So the first event you can see, we need to create two events, the start event and a stop event, using this command CUDA event create, using this function, not a command, I would say. This is a CUDA, or maybe it can be a macro as well. I have not looked into it, but it looks like a function which returns CUDA error T, if I remember correctly. Now we start recording of the start event. So now we have put it into the GPU stream that start working on this. Start recording the start event. It is confusing name as well. Now we are calling the kernel. Now we will see a strange call to a function called CUDA device synchronize, right? Now sometimes it may happen is, so how CPU does is, CPU will tell the GPU that do your stuff, and GPU will try running it in the background, and CPU may exit before GPU finishes. It exits first before GPU, and that is a bad stuff. We don't want to do that. We do not want to execute before GPU finishes the task. It is bad look on us as well as the kernel program. Now, uh, so what we say after writing CUDA device synchronize, we tell the compiler that please, CPU, please, can you please wait for the GPU to finish? It would make sense if you could wait. Otherwise, it may break something. It may break something, and that is not good. So CUDA event record stop. We started with the event, then we started recording the stop event as well, and now we are finally doing a similar thing for the events, CUDA events synchronize, where again saying to the GPU please finish, or the CPU please finish all your tasks before moving further. Please make sure that the stop event has been synchronized and it has been recording. Now we can print out the time elapsed using this CUDA event elapsed time, and passing it your passing the reference of your elapsed variable and start and stop events as well, and it will print the thing nicely. And you need to destroy your allocations. So in this case, you allocated start and stop. Please destroy it. Right? Why do you want to waste your memory? So I hope you understood the first example as well pretty well. This is the easiest thing you can have. Basically, you don't need to have a lot of this stuff. So let me, this is not required, this is not required, and this is not required. So if you just want to say what your hello world can be, you can also write it. Sorry for all the errors, and it might be confusing. And how will you calculate? Sorry, this should be n plus 256 minus 1, right? Because the number of threads per block is 256 minus 1. Let's say and divide by 256. And here we can simply specify 256 as well, which will say this is our threads per block. And then we can remove these two lines. This is this is a very simple hello world that you can have. It will also result in the same thing, but you don't have the timing kernel as well. I will not save it. Let's say. Okay. Now, moving on to the second example, which is an interesting one and which you might be also aware about. So one of the basic things to do is do a vector addition in CUDA, right? The first things that people do. we'll observe that I have defined a kernel. I don't want to write this event start and all of that stuff again and again. So I just wrote a time kernel macro. It is called a periodic macro. And how it works is, if you go down, you will see that I can just write time kernel and specify my kernel along with all the parameters, and it will print nicely what is happening. So how this code works is, we have defined our imports, and now we are defining our kernel as well. So the kernel is again using the global keyword, telling our compiler that this function, this kernel is to be run on GPU and can be called from CPU. We have the name vector add, and it will take four things: a, b, c, and an integer n. N would be the size of the array in that case. So a and b needs to be added together, and the result has to be stored in c. So to find out the unique index of a thread, such that we can see if it is in limits, if it is below n or not, you can always use this formula: block idx dot x times block dimension dot x plus thread idx dot x, right? If you have a 2D index, if you are working with matrices and you want a I and j, you can use block idx dot y, replacing x with y everywhere, right? Same goes for if you are adding another dimension as well. You can have z or z for American and US differences. Not that anybody of them would be watching, because nobody watches these videos, not even my own family, which is sad. Okay, that was a little bit strange. Now, this is pretty simple stuff in the vector addition. We are just checking if the index is less than n or not, and then we are storing the results in C. Now, now you will observe that there are a little bit of A, B, and C and N involved, and we need to allocate and free the memory as well, because we are pro developers. We manage our memory on our own. We don't rely on safe languages. Now, there are millions of elements, and the size of the memory that requires to be allocated is n times the size of float, which I guess would make sense. Then we are allocating memory for A, B, and C. All of them would be of n elements each. Then I am just initializing A and B array with some values. So A will have 0, 1, 2, and up to n, and B will have 2 times the integer I. Now, these A, B, and C array are to be used on host. They are host managed arrays, which in our case is CPU. Then we are also declaring, let's say, three arrays: DA, DB, and DC. Now you will observe that for A, B, and C, we used malloc, but if you're allocating any memory on device, you need to use the function, the memory allocator function provided by CUDA, which is CUDA malloc. It is pretty easy to understand. You just typecast is to void double pointer and then pass in DA, DB, and DC and the size of it. It's pretty much the same thing, except you are just passing in DA as well. So what it returns is, it does not return anything apart from the CUDA error. So if you want to check the terms, you can find it on the, I'll try to paste it in the description about CUDA errors. Now, what we want to do next is, let me explain it in here. That would make much more sense. So you have your CPU, you have declared arrays A, B, and let's say C. You have your GPU, you have device arrays DA, DB, and DC. What we want to tell the GPU, or what we want to do with these arrays, we don't want to perform any operation, not even addition, simple addition on CPU. That would make this things hella slow. So we copy all these arrays to these counterparts, DA, DB, and DC. And after copying, we call the kernel, we do our operations. What the hell has happened to my writing? We call the kernel. Once it has done its operations, the output array in this case is DC. So what we do with DC is, we copy it back to C, which is on host, in our case, the CPU, as well as in this case, it will be GPU, right? So this is the basic operation of it. You declare host memory, you declare device memory, you copy some of things from host to device, you copy some of them back after calling the kernel, and then you validate the results do whatever you want, right? So CUDA malloc is allocating size amounts of memory required to DA, DB, and DC, and we are now the important part. We're using CUDA mem copy to this is the destination. DA is a destination device array. DADB is DADB are the device arrays. The source arrays are the arrays declared on host on CPU, which are A and B. We are mentioning the size of the data that we need to copy, and one of the most important flags here is CUDA memcopy host to device. So there's a flag that says that we are copying this particular memory from host to the device, from the CPU to the GPU, which makes sense, right? We're copying from A to DA. A is on CPU, DA is on GPU. Then we are doing our usual stuff. We are defining our threads per block as 256. Then we are trying to calculate the appropriate number of blocks that would be required. We are calling our kernel vector add with blocks per grid and threads per block with the required parameters, which in this case would be DA, DB, DC, and N. Now we are calling CUDA device synchronize, which I hope you understood that CPU should not exist before GPU finishes all the operations, and it should basically do its task first before telling the CPU, okay, I'm done. No, it does not work like that. Then after the kernel job is finished, we have synchronized the hell out of it. We are copying the results stored in DC to the host C, from where we can just check the output, evaluate, or view or print whatever we try to do. Now, if you will see, the source is DC and the host is sorry, the destination is C, and the flag has been changed to CUDA memcopy device to host, where earlier it was host to device. So there is a little bit of difference in there, but important difference. Now we are just printing the elements in C in the array C. Now you have used malloc for these three and CUDA malloc for these three. So basically you are allocating memory, right? And if you're taking something, you need to give it back. In this case, you are taking the memory from your operating system. Please give me some memory. You are begging for it. Basically, it is a machine, but you have to beg for memory. So you are saying free the memory. You can use it again. Free the memory GPU. You are the boss now. Please free DA, DB, and DC. Same goes for CPU. We are telling please free A, B, and C. Now you're free to use this particular address in the memory. It is not allocated. It is fine. Yeah. So let's try to run this again. Hmm. So it will say time taken by this particular kernel is this the seconds, and you will see also see the results as we are printing in the code later on, the first five elements 0, 3, 6, and 9. So you can do all of your validation stuff as well. So this is the first lecture in the series. I hope I tried to explain, I hope I have explained it pretty clearly. But if not, maybe you can forgive me because I am not an expert in this field, but I try to explain the things as clearly as possible according to my own understanding. Right? I don't want to understand a lot of details without trying to explain it to a very, let's say, beginner person, which I am too. Ending this, the topic for tomorrow, maybe we will be implementing a matrix multiplication and iterating it uh, and try to improve it. So we'll see a lot of different things and try to see how we can improve matrix multiplication. I'm not saying that we will reach the level of CoBLAS or highly optimized libraries or previous implementations of it, but we will basically start from the beginning, start from the naive general matrix multiplication, and try to improve the benchmarks. We'll also try to see roofline analysis as well and some sort of matrix that we can track.